Hello, in this video we're going to attempt a 2D fluid flow through a mechanical heart valve, and the mechanical heart valve has some leaflets that rotate through about a pivot, and when the pressure is going positive on the pressure difference between the inlet and the outlet is positive, the valve is open, and when the pressure difference becomes negative, the flow reverses and the valves will swing to the closed position. And so I've prepared a initial mesh object that I'm going to show in the video how to get some fluid flow simulated. And what I have is some named selections: the inlet, the outlet, and then the leaflet on the positive Y side of the center and the leaflet on the negative Y. So those are named selections. The mesh is just an all triangle method because we're using dynamic meshing to allow the fluid to push the leaflets open and closed. So we start out by adding Fluent to the mesh object and updating the mesh, and then opening Fluent on the setup. Fluent notices the geometry was 2D, that it was in the mesh. So we're going to do double precision and start. So Fluent has provided us defaults, turbulent flow model, but I'm going to run this laminar just for purposes of the demo today. And we automatically get air as a fluid, but I'm going to overwrite the air with properties for blood, and so that is a density of 1060, close to water, which is around 1000, and a viscosity of 3.5 e to the minus 3. That's the viscosity of blood. I could potentially edit the material name, well, maybe not. Anyway, doesn't matter. It's got the correct properties. Initially, I'm going to solve this without the fluid, without the leaflet motion, just as a steady state solution to get the initial distribution of velocity in this volume. And it's already a planar model. So let us go ahead and set up boundary conditions. So on the inlet side, currently it's set for a velocity input, but we want to right click and change the inlet type from velocity to pressure. And then we'll set a inlet pressure of 1000 Pascal. And the outlet pressure is always defaults to 0. And so it's the pressure difference that dictates if the flow is going to the left or the right. So we'll just keep the pressure difference. And with that, we can do an initialization. And the initialization could be maybe a standard, and just take half the pressure and guess on a velocity, I have no idea. We'll initialize that, and then we'll go ahead and run some calculations, say 300 steps, and see what we get at the end of the steady state simulation when it's finished running. So here we see the residuals, and it has converged. And what we want to do now is insert some results. So we want some graphics, we want maybe a vector plot, and this will be velocity, and we will just compute that, and we've got a velocity of 2 meters per second. So what that's telling us is that's potentially too high of a initial pressure. We're expecting something less than that, so I'll go back and change the pressure to a lower value. I'll cut it in half. Apply that, close, and then we'll go back and we'll just calculate 300 more steps, and maybe let's initialize. Let's go ahead and initialize then. Might turn off the sound. We don't need to hear that banging on our ears. So in the solution branch initialization, I'm going to initialize, throw away that result, and now calculate. Oh, I just thought of a different way to get to home in on the, I could set the velocity I want, which is around 0.8, and then measure the pressure at the inlet. So that's still way too much pressure. So let's do the inlet, set the inlet type back to velocity, and or better yet, set the outlet. Yeah, we'll set the inlet velocity to 0.8, and we'll ask for a report. We'll have a new report. We'll have a surface report on the area weighted pressure. Area weighted inlet pressure. And that's the static pressure at the inlet. Okay. Now we can go back to initialization and initialize, and then run a calculation. So while the peak velocity is 1.22, the average velocity at the inlet um, is by boundary conditions 0.8. So what we want to do is look at that report, or just scroll up here a bit. Yeah, look at that report. Well, go to the results section and look at the surface integral area weighted average at the inlet at pressure, there we go, of 18. So we're going to use a pressure difference of 18 Pascal to generate an average velocity at the inlet of 0.8. So that's good. We'll use that down the road. So this is a useful initial condition for a transient, and I'm not too sure if it's as simple as changing to transient and starting the solution after I've built in the other pieces of the model, namely the dynamic mesh pieces. Let's see if I can do that. And here is the dynamic mesh that is being turned on, and we want to allow remeshing. We want to enable 6 degrees of freedom on 2 of the leaves, and so we need to create a 6 DOF property, which is leaf on the positive Y side with a mass of 0.1, 0.01 with rotation, and the center of rotation is just in there somewhere. I have the coordinates in this file. Here are the coordinates. X is minus 0.0204 and Y equals 0.00197, and it's constrained to only travel 64 degrees, and then it can't travel any further. And 0.001, I'm just making up numbers for mass and moment of inertia. So that is the positive Y. And note when it hits that limit, there's still a gap at the centers and edge. So we also need a negative Y property, and the only difference is it's on the negative side of the Y-axis, but it can go minus 64 degrees up to 0, which is its fully open state, which is where it is now. So now with those two properties defined, we can use them to create dynamic mesh zones, and that is a rigid body on the positive, using the positive property, where the center of gravity location, we'll just estimate that in as minus 0.01 and close enough to 0. And we will say create, and then we want to create a negative y on these edges using the negative y properties, and same center of gravity, create. So there are our two dynamic mesh zones. I think we'll just see what else. Yeah, that's all set, and that's all set. And we'll eventually set a sinusoidal function on the pressure. So we'll grab this text, which might become useful soon, copy, and go back to the input boundary condition, inlet, and go back to a type pressure. And the pressure is going to be an expression, and the expression is going to be that text I just copied. Apply. So there's close. There's our pressure. Yep, close, and the outlet is still at a 0 pressure. Got our interfaces, and back to general, we're going back to transient. We're going to transient now. So with transient, that time, t equals time, that's meaningful. T over 1 second takes the units out of that, so the sine function can operate on numbers. So a couple of more things we want. We've got this plot. What we want to do is turn off all these ranges, and we'll go up to the 1.25 limit that we saw for this to be a constant legend while it's running the transient. And we'll scale this down. I think that is good. Let me check. Maybe 0.043. We'll see how it looks. We might have to rerun it later. The color map also, we'd prefer it to be on the bottom. And the color map maybe could be a little bigger. Close, and we'll do filled arrow. We don't want compute, we want compute takes it from the results, 1.25. So we're going to save that, close that up, and before you run a solution, if you want animation. You have to set up the animation before you run the solution, and that is under the solution, animations, new, an animation of the velocity, and instead of time step, we'll do flow time 0.002, and we want vector velocity. Okay. The other thing we're going to do is under view, we're going to zoom in a little bit here. And that under views, we can save the view name. So view 0 is the view we want to be as zoomed in a bit. Otherwise, it'll be that small thing we were looking at before. So that's the animation. There's a way to create a scene, which may be an advanced topic. I'm going to skip that. This is good enough for now. So we will see if that is good enough to run a calculation now, where we're going to go for 1,500 time steps of 0.001 second increments, and we're going to get 1.5 seconds of simulated time. So let us hit calculate and see if I remembered to put everything in. Okay. Okay to overwrite. Yes. So we'll come back when it's done. Well, we can see the plot of the inlet pressure dropping. And so after half a second of simulated time, the pressure will be 0, and then it'll go negative and the flow will reverse. Checking in on how it's going, and I'm looking at the inlet pressure and realize that I have forgotten to take that information of the 18 Pascal and replace the 1000 at the start of the pressure equation with 18. So I'll be discarding this run and doing it over with 18 in the front of the equation, but that'll be for the next video. Here we'll see how the results look even though the pressure's way too high. All right, so we'll see if we can get anything useful in the animation on a playback. And there it is, the sequence, and 750 frames, which is every other frame of the 1500 frames requested, and we'll write those frames out to a file. I guess that is done. I see under the right format, we don't want frames, we want a video file, and that's the video name, and now I'm going to write that out, and it's writing the video. Here's the video file. Let's see how it looks. Looks pretty good. Oh, now it's back to 0. So not quite a perfect loop, but can work on that some, I guess. And need to rerun it again anyway because I put in too high of a pressure. So I guess that's it. The end time is 1.5. All right, there it is. Bye.